Hi, everybody. Welcome to the AOML Virtual Open House. My name is Heidi Van Buskirk, and I'm going to be moderating today's webinar. This series is brought to you by NOAA's Atlantic Oceanographic and Meteorological Laboratory, or AOML, in Miami, Florida, and it's designed to help you get to know AOML and some of the incredible experts that we have here at our lab. To celebrate Earth Day this year, which is on April 22nd, we're bringing you an inside look at some of the groundbreaking research our scientists are doing. Throughout these webinars, we'll explore hurricanes, ocean currents, extreme weather, and coastal ecosystems. Today, we'll be exploring the exciting world of oceanography and how we monitor our oceans. We have a few guidelines before I welcome our first speaker. You're all muted because we have a lot of people on the line, and we want to make sure everybody can hear our speaker. However, there is a questions box on your GoToWebinar panel. Please write your questions for our speakers there. We encourage you to ask questions as we go along, and our speakers will be taking time to answer them at the end of their presentations. We may not be able to get to all of the questions, but we will do our best to answer as many as possible. Without further ado, it's time for me to turn it over to our first speaker, Rick Lumpkin.
Thank you, Heidi. Let's see. Can you see my screen?
I am going to send you access now, and you should be able to share your screen.
There we go.
All right, take it away, Rick. Thank you.
You bet. So I am a physical oceanographer at AOML. That means I study the physics of the ocean. In my case, I am focused on ocean currents, which I'll talk about a little bit later in this talk. There's a number of reasons we want to observe the ocean. We want to have better weather forecasts. These observations help improve the forecasts. They help us to understand how the ocean is changing at climate timescales, how it affects the economy, and allow us to do a better job of doing search and rescue for mariners at sea, responding to oil spill, and understanding where objects floating in the ocean are going. We observe the ocean typically from vessels like the one you see here. This is a NOAA research ship that a lot of us have been on to collect measurements of the ocean. You can see a group of oceanographers carrying their suitcases on the left here and getting ready to go out to sea, sometimes for as long as a month, collecting ocean observations. We use a lot of different instruments that we place into the ocean to measure the ocean. Here you're seeing a moored buoy, or just a mooring. It's a buoy that floats at the surface, connected by a long cable to an anchor that we drop down to the bottom of the ocean, and it stays in one place. These particular buoys measure the atmosphere, they measure winds, they measure humidity, they measure solar radiation coming down, and then on that long line extending down into the ocean, they measure ocean temperatures and salinities and ocean currents. These particular buoys are part of a global array that spans around the world. You can see the little dots in this map at the bottom showing where the different moorings are located. This is another instrument that we have called a conductivity temperature depth, or CTD as we call it. We lower it down into the ocean, and as it's going down and coming back up, it measures temperatures, and it measures how much salt is in the water, and it measures ocean currents. And also it has these plastic tubes, those gray tubes that you see, which snap shut at predetermined depths and collect water samples. And on the right, you can see a group of us actually taking water from those samples to measure things like how much oxygen is in the water. In addition to objects that stay in one spot, like the moorings, we have a number of instruments that float around. This particular instrument here is called a drifter. It's a drifting buoy that's tracked by satellites and measures temperatures and measures barometric pressure for improved weather forecasts, and it measures ocean currents. We have an array all around the world. You can see in this map at left, and they're deployed by lots of partners all around the world as well. Lots of different countries help us put these drifters into the water. Another drifting instrument is called an Argo Float. You can see Grant and I lowering one down into the water here, and what the float might look like floating at the surface before it dives down beneath the ocean surface. So these are basically little robots that go up and down measuring the temperature and salinity miles down into the ocean. Another instrument, Vanellos deploying one on the right and me on the left, is called an expendable bathythermograph, or just XBT. As these drop, they measure temperatures, so we can see how the ocean changes and its temperature is from the surface down to many, many hundreds of meters beneath the surface. Grant will be telling you more about gliders. These are robots that we actually steer from the laboratory or from home on a phone. They dive up and down, measuring a number of different properties, and they improve hurricane forecasts. We fly them during hurricane season. By fly, actually, we have them drive through the ocean. This is a relatively new instrument. It's called a sail drone. It's basically like the gliders, remote controlled, but instead of diving up and down, it floats at the surface and it sails, getting power from the solar panel you see here and from onboard batteries, and measuring both the upper ocean and the lower atmosphere. And we don't only measure the ocean while we're out at sea, we also collect measurements of the atmosphere. Here you can see a student launching a balloon, and as the balloon goes up into the atmosphere, it measures a number of different properties like the temperature and the humidity of the air. So we collect measurements both of the ocean and the atmosphere, so we can see more how they work together, something you'll be hearing about from Shen Fu later in these talks. And we don't just put objects in the ocean, we also observe the ocean remotely from satellites. Here you can see different types of satellites and some of their measurements. Satellites can measure things like the temperature of the ocean. They can estimate the salt of the ocean. They can even tell us how high the ocean is, so we can see how the sea levels are changing through time. There's a lot of different reasons that we would like to study the ocean, and one of those reasons is illustrated here. We want to understand better where sargassum is coming from and where it will go. Sargassum is basically seaweed. You see a picture of it at left, and you've probably seen this at Miami Beach or other beaches that you've been to. In small amounts, it's perfectly fine. It's natural, and it's something that a number of creatures use as their habitat. The problem is when things happen like what you see on the right. There's a beach underneath all that sargassum, but it's been completely buried. This is a problem that started happening in around 2012 in a number of islands in the Caribbean and along the coasts of Mexico and now in the United States. We want to understand why that happened, what changed, and when we see a lot of sargassum from satellite pictures, we want to know where it's going. So at AOML, we've done some studies really focusing at where objects move in the ocean. You can see pictures of some of the drifters that we designed specially for this effort here. Some designed to move like floating pieces of ocean debris, like on the left. And in the middle, you see a mat that's designed to float like sargassum. And then we track these by satellite and we follow them around. The objects move as they're carried by ocean currents and also blown by the wind and pushed by the waves. By studying their motion, we can understand how those different forces move the objects, and that allows us to better forecast where objects floating at the surface will go in the future. From looking at all these different types of observations, especially from these drifting buoys, we can make a map of the ocean currents all around the world. These are like rivers in the ocean, moving water from one place to another. At the surface, the oceans look like this, the ocean currents look like this, and have all these different names. But really, they all connect up into this one big complicated system of currents that wraps all around the world. Right off of Florida is one of the major currents of the world, known as the Florida Current, which carries between the Miami and the Bahamas about 30 million tons of water per second northward. This is warm tropical waters passing north into the North Atlantic. When we look beneath the surface, we can see that the ocean current system is a complicated three-dimensional picture. The red arrows in this diagram are the ocean surface currents, but the ocean currents reach high latitudes near the north and south poles, where the water becomes cold and sinks, and it goes down to become these blue currents, down deep beneath the ocean, miles beneath the surface, that slowly move back away from those high latitude regions, slowly warm back up again, and pass through the greens and yellows and back up to the ocean surface again in reds. This overall system is 1,000 years for a particle to travel around the world from the surface down to the ocean depths and then back up to the surface again. We call this the Great Ocean Conveyor Belt. And it is a three-dimensional picture then of how the ocean currents connect up the entire world. That concludes my talks, and I'd be happy to take any questions you may have.
Thank you, Rick. Awesome presentation. We do have a couple of questions here. Starting off, somebody is curious about the CTDs. They want to know, how deep do CTDs go?
That's a great question. We can lower them down to a specific depth if that's what we're really interested in, but very often we actually go all the way. Let me bring up the picture of this. At CTD, there it is. Very often we take it all the way down to the very, very bottom of the ocean, which can be, like 5 miles deep in a lot of places. And it takes quite a while to get that deep. We can basically, from the time we put it in the water to go down, reach the bottom of the ocean and bring it back up again, very typically 3 or 4 hours have passed.
Very cool. And we have a couple more questions about sargassum people are interested in. One of them being, how long does sargassum live in the ocean, and does it sink when it dies?
Sargassum tends to float because it has, and if you can see in the picture on the left, those little bubbles, those are filled with air. And so even if the sargassum itself was completely bleached by the sun and dead, those individual bubbles would have to be broken by, say, someone popping them or a ship hitting the patch very hard before it would sink. So it tends to float and then tends to run aground. Now, what happens with most sargassum, especially before so much of it was washing up on the beaches, is that it accumulated in the centers of the ocean where the winds tend to push things together. In fact, the part of the North Atlantic where this collects is called the Sargasso Sea as a result of all the sargassum.
And does sargassum have any benefits for marine life?
It absolutely does. And in normal quantities, it serves as an environment for small fish to evade larger fish. Creatures such as crabs and shrimp live inside the sargassum. And so there's an entire community of animals that are dependent upon the sargassum to protect them. Also, in smaller amounts, it serves to help protect sea turtles as they nest and lay their eggs, and the babies hatch and come back out again. On the other hand, if there's huge amounts of sargassum, like you see at the right, that can entangle the baby turtles, and even the adult turtles can become entangled, and it can threaten their lives. So it can be both positive and negative.
All right, and we have one last question. Does sargassum have any beneficial uses, like for fertilizer for plants?
I think that's a problem that's being looked into as one way of solving the problem of all of this sargassum being deposited. If you just simply picked it up and threw it back into the ocean again, a lot of it would simply wash back ashore. So people are investigating ways of using this for mulch, for filling areas that we would want to fill and such. It's a problem that needs to be studied because along with the sargassum can be some chemicals that would be at background levels not concentrated, but if you were to concentrate a lot of it in an area, it may have negative impacts as well. So this is something that our colleagues in the Ocean Chemistry Division are considering.
Very cool. We'll be interested in keeping up with some of that research as it comes out. Thank you, Rick, for your presentation. And I'm going to pass it off to our next speaker, Vanellos Perez, and she has a density experiment for us.
Hello, everybody. Can you see me okay?
Yes, we can.
Okay, fantastic. I'm going to show my screen. Hopefully all of this is working seamlessly. Can you all see my screen? Okay, fantastic.
Yes, we can.
So my name is Vanellos Perez. I'm a NOAA physical oceanographer, and I'm going to be talking to you today about how seawater density drives ocean currents and what controls the density of seawater. So a little bit just about myself. I grew up in Miami. My family immigrated to Florida from Cuba. And so I grew up surrounded by the beaches and the ocean. And as a teenager, I realized I liked math and physics. And so that sort of set me on the course of studying physical oceanography. I did my undergraduate degree at the University of Miami and then my master's degree. And then I went and got my PhD at Oregon State University. Some of the things that I love most about my job is being able to work with an amazing team of really incredible, smart people. I love working with them to solve science puzzles. When it's safe to do so, I like going into the field and doing research, which is a picture that I'm showing on my slide. And I like doing outreach and talking to students and people that are interested in science. So today what we're going to do is 3 quick demonstrations that illustrate what controls density and how that can drive ocean currents. And so when I talk about seawater density, what I'm talking about is its mass per unit volume. So it's like how much stuff is compressed into a certain volume. And it turns out that in the ocean, seawater isn't doesn't have a uniform density, and it doesn't have a uniform temperature, and it doesn't have a uniform salt content or salinity. And in fact, that is what drives a lot of the ocean currents that Rick was discussing in his previous presentation. It turns out that seawater sorts itself into density layers, with the lightest layers being at the surface and the heaviest layers being at the seafloor. And that is because of gravity. And because the layers are not flat, they're tilted, that drives ocean currents in the global oceans. So think of a hill, and you put a marble at the top of the hill, the marble is going to roll downhill. So the same thing with water. It's going to flow along these tilted density surfaces. So I'm going to do some demonstrations today, and hopefully I'm going to stop sharing my screen and this will work. Let's see. Are you no longer seeing my screen?
We can still see your screen, Vanellos.
You can see, but do you see my presentation or?
We can see your your desktop screen. We can also see you in the webcam.
Okay, I'd like to stop sharing my desktop
there you
screen.
Go. Now we can just see you.
Okay, perfect. Thank you. I should have practiced that before.
No worries.
So hopefully you can see a tank that I've set up. Can you see it all right?
Yes, we can.
Okay, so the first thing that we're going to do is a demonstration of how the temperature of seawater can affect the density. And so I have a tank here that has a separator, and I've got warm water that I have put food coloring in. There's nothing special about the water. It's just like half boiled water and half room temperature water so that it's not scalding. That's a very important step. And I'm putting it in one side of the tank. And then I'm going to put in the other side of the tank water that's been in the refrigerator, and it's food colored blue. So there's nothing special about these two waters. They're just cold and hot. Okay, so I'm going to remove this separator, and this is going to show us what a temperature difference can do, in terms of density and ocean currents. So if people want to use the chat and speculate as to what they think is going to happen, that would be fantastic. And this is going to illustrate sort of what Rick was talking about what's happening. Think of this as the Atlantic Ocean in a box. And this is the equator, where you get more heat from the sun on average. And this is the North Atlantic, where you get less heat from the sun on average. And so this is going to kind of illustrate what Rick was talking about in this upper, near surface circulation and deeper circulation. So did anybody put in some comments in the chat?
Yeah, so some people are answering, and they are saying that the cold water they think is going to sink to the bottom. Some people think the hot water is going to sink. Some people are saying that they might mix. That a lot of different answers.
All right, so let's see what happens. Okay, dun, dun, dun. Let's see if I can lift it in a streamlined way. All right, so somebody did say what the right thing that was going to happen was. What happened was the blue water is actually, the cold water is actually more dense or heavier than the warm water, the red water. And that's because when you warm water, it expands and so it becomes less dense. And when you cool water, it contracts and it becomes more dense. And so what we saw was the blue water sank below the red water and went from think of this as the North Atlantic towards the equator. And the red water was lighter and it floated on top of the blue water, and it went from the equator to the North Atlantic. So think of this as the Gulf Stream bringing warm water by Florida all the way over to Europe, and think of this as the deep circulation that's underneath the Gulf Stream. And so the take home from this is that temperature can affect the density of water. And so, the colder it is, the more dense it is, and it can drive ocean currents. Having a temperature difference creates a density difference, which drives ocean currents. And it's really fascinating. I wish you all were here in my kitchen. Maybe it would be a little crowded, but if you put your finger all the way down through the tank, it's really uncanny because you feel this cold water at the bottom and warm water at the top. And even though that's what you're going to feel, you don't know until you feel it viscerally. So if I left the tank alone for about an hour, the temperatures would equilibrate, and then the prediction that somebody made that everything would mix and it would become purple would come true. So if I just let that sit for an hour, we'll come back to it, and it would be purple in there and all the same temperature. So now we're going to look at what happens with salinity. And so here I have room temperature water that's fresh, and I put blue food coloring in it. Okay, so there's nothing special about that water or any of the water, really. And then I put yellow food colored water that has salt. So I just took, table salt and put it in there, but you could do this experiment with seawater. So they're the same temperature, and the only difference is this side is salty and this side is fresh. So what do people think is going to happen in this tank when I remove the separation?
Right, you can go ahead and type in the chat box what you guys think is going to happen in this density experiment. We're getting a couple of answers in. A lot of people are saying that the salt water is going to sink to the bottom and the fresh water is going to rise to the top.
Okay. All right. All right. So
Somebody said they think the fresh water might sink.
Okay. Do they think it's going to make, some people might think it's going to mix and make yellow and blue will make green, which is also possible. All right. So let's see what happens. I'm going to remove the partition. Remember, salty, fresh. Okay. So somebody predicted correctly. When you remove the partition, you see that the salt water is indeed denser than the fresh water. And that's because we took a solid salt and added it to water and made a new solution that has a higher density than the fresh water. And so the salt water went from, we created 2 layers in the tank, and we created a current from one side to the other, with the light flow going from right to left and the heavy water going from, I can't do directions backwards, from this side to the other side. I shouldn't say right and left. And so the take home point here is salinity can affect density and it can set up ocean currents. And if I put the partition back, I'm going to do a third last final experiment. I'm going to mix this side, and I'm also going to put in 2 drops of red food coloring. So we're going to see what happens. So I'm basically taking that low density water and heavy density water and mixing them and creating a new water. So what do people think is going to happen when I remove the partition now? So we've mixed those 2 waters together.
All right, a lot of people are saying that they think that it's all going to mix and just become a bunch of brown water.
That is possible. That is possible. When you add too much food color, it definitely does that. All right, so I think I'll go ahead and do the big reveal. Aha. So what we see is quite surprising. There is a lot of brown water in there, but that medium density water that we created when we mixed the low density water with the high density water made a 3rd layer. And rather than that 3rd layer being at the top or the bottom, it went right into the middle. And so this is illustrating that in the real ocean, first of all, there's no food color, but we have really a continuum of layers. It's not 2 layers, it's not 3 layers, it's just a bunch of layers of different densities, with the lightest at the top, the mediums in the middle, and the heaviest at the bottom. And in the real ocean, you also have competing effects. So you don't have all fresh water, all salty water, all cold water, all hot water. You have, temperature changes and salt changes affecting the density at the same time. And so when Rick said we use the CTD and we lower it down 3 miles deep, we're really, lowering that instrument through all of these layers, trying to measure the temperature and salinity in all of those layers and the velocity of the water in all of the currents in all of those layers. So I'm finished with the tank, and if I can share my screen one more time, let's see if that will work. It might not. Are you all able to see my screen, my presentation?
We can't see it right now.
Oh, I need to have the share my screen set up, or?
Oh, you should just be able to press start.
Let's see. Okay, did that work?
Yes, it did.
Okay, fantastic. Oh, no, one too many. Okay, so this is my last slide. So basically, I just wanted to make the point that when we lower that CTD and we sample through all those layers, if you're 3 miles deep, you have all of that water on top of you. And you can think about when you dive in a swimming pool or something like that and you swim to the bottom, you feel the effects of the pressure of the water on top of you. So imagine 3 miles of water on top of you. And so I can't illustrate in my tank, unfortunately, my little tank here, what pressure does to density, but pressure also can affect density. And I illustrate that by showing you 2 styrofoam cups that I colored on a cruise that I was on. And one of them I attached to that CTD frame, and it went down 3 miles deep and came back up. And you can see the effect of all of that pressure of the seawater above you shrank that cup, so that it's, you know, really, really like a miniaturized version of the cup that stayed on the ship with us. And so that is just trying to illustrate what we can't illustrate here in my kitchen in the little tank, that density is also affected by pressure. And so there's 3 things that affect the density of seawater. That's temperature, its salt content, and pressure. And it causes us to have layers that are stratified from lightest down to heaviest, and those layers are not flat, and that drives ocean currents. And so with that, I will turn things over for any questions, but thank you very much for listening to me.
Awesome. Thank you so much for that demonstration, Vanellos. That was very interesting. We do have a couple questions coming in the chat, if you don't mind answering them.
Sure.
Let's see. I think we'll start off. Somebody is wondering, how does circulation work around Antarctica?
So around Antarctica, there are no land masses to constrain the flow. So you have an Antarctic circumpolar current that can flow the whole way around Antarctica, and you know, and all of the water can eventually make it from one part of the ocean to the next, but land can provide a barrier, so it can, you know, the water has to go around that land. So hopefully that answered the question.
And somebody else wants to know, what would happen if ocean circulation stopped?
So one thing I didn't talk about is that these ocean circulations, these currents, when they move, they carry with them their heat signature and their salt signature. So normally the Gulf Stream, you know, moves warm water past Florida all the way over to Europe, and that's one of the reasons why it has a mild winter, because it's bringing all of that warmth that is released into the atmosphere and then makes the winter there, you know, more temperate. So if ocean currents stopped, it would affect the weather and climate of all of the surrounding continents, because areas that normally get warm water brought to it by ocean currents, or areas that normally get cold water brought to it by ocean currents, that would you know, change. So
Cool. And I believe we have one last question. And somebody is wondering, why are some currents stronger than others?
So when currents can be stronger than others because of different winds, you know, you can have stronger winds that can drive stronger currents, but you can also, thinking back to our experiment here, the stronger the density difference, the stronger the currents, for the currents that are driven by density differences. So if you have, you know, 96 degrees Fahrenheit water and 95 degrees Fahrenheit water, it's not going to drive a strong current. But if you have, you know, 100 degrees Fahrenheit, well, that's pretty warm. If you had 95 degrees Fahrenheit water and you know, 40 degrees Fahrenheit water, that's going to drive a stronger current if you have a big temperature difference or a big density difference.
Very cool. All right, thank you so much for your presentation and your demonstration, Vanellos. I'm going to send it over to our next speaker, Shenfu Dong. She's going to be talking a little bit about how currents drive changes in weather.
So can you see my screen?
Yes, we can. Take it away, Shenfu.
Okay. So I'm Shenfu Dong. Thank you all for joining us today. Working the NOAA AOML Physical Oceanography Division. Just before my talk, just a little bit about how I became a physical oceanographer. I grew up in China. When I was in middle school and high school, I loved physics, and the ocean is very mysterious to me. I was interested in applying physics to understand some of the mysterious ocean phenomena. I got my undergraduate and master degrees from the Ocean University of China and came to the US to gain a better training, and got my doctorate degree in the University of Washington in Seattle. So today I'm going to talk to you some of the things I have learned throughout the years about ocean transport, how it impacts our climate and weather. As you know, we live on a blue planet. 70% of our planet's surface is covered by water, and 97% of water, liquid water, is in the ocean. Compared to air, water has very high heat capacity. This gives the ocean the ability to absorb much of the solar energy that reaches Earth's surface, and it can release enormous amount of heat without a larger change in temperature. In fact, the top 3 meters of the ocean stores more heat than the entire atmosphere, and the heat stored in the ocean can keep our planet warm for decades. So ocean is constantly moving, as you have learned from previous talk, and through currents, the ocean transports heat from one region to another and release it back to the atmosphere. And this tremendous ability of ocean in absorb, distribute, and release heat over a long period of time gives the ocean a central role in regulating and stabilizing our climate and weather system. So how does the ocean transport impact global temperature distribution? Solar energy reaching Earth's surface is unevenly distributed. The equator receives the most solar energy over a year, but much less solar energy gets to the poles. As a result, there is a net energy surplus in the lower latitudes because the solar energy absorbed is greater than the heat radiated. On the contrary, there is a net energy deficit in higher latitude. Ocean currents counteract the uneven distribution of solar radiation by transporting warm water from the equator toward the poles and cold water from the poles to the equator. This ocean transport makes a large part of our planet livable and generates different climate in different parts of the world. For example, as Vanellos mentioned, in the northwest Europe, in spite of its higher latitude, has a much mild winter because the Gulf Stream off the US East Coast transporting warm water north to those areas. Without ocean transport, the uneven distribution of solar radiation will make the equator too hot and the poles too cold to live. Ocean transport also plays a critical role on global rainfall pattern. Ocean water is constantly evaporating into the atmosphere as water vapor, and it becomes part of the clouds and drifts off with winds, eventually drops to the ocean or land as rain or snow. Almost all rain that falls on land starts off in the ocean. How fast the water evaporates is influenced by water temperature. The warmer the water, the greater the evaporation. Therefore, the distribution of ocean temperature helps to shape the global rainfall pattern. In general, we see more rainfall in the equatorial region and off east coast of continents where the ocean temperature is high. Ocean also impacts the ocean also plays an active role in short-term extreme weather events, such as drought, floods, storms, and hurricanes. For example, ocean acts as a heat engine that helps to fuel the growth of a hurricane. When a hurricane passing through warm water, it gains wind speed. Vice versa, a hurricane loses wind speed when the ocean water below is cold. For example, when Hurricane Katrina moved over the warm water in the Gulf of Mexico, its wind speed increased from 115 to 173 miles per hour. So like winds in the atmosphere, currents in the ocean are constantly changing. For example, the Florida current, the name given to the Gulf Stream as it passes through the Straits of Florida. We have observed large changes in the Florida current transport over the past 40 years on timescales days to decades. So changes in ocean currents redistribute ocean heat that causes temperature in the ocean rise or fall in different regions. Those changes in ocean heat and temperature will cause change in weather pattern and also a climate pattern regionally and also globally. For example, in the South Atlantic, a strong Brazil current brings more warm water from the tropics, which warms the subtropical region. And this warm anomaly forces more evaporation, and the water vapor flows off with wind to the southeast Brazil and causing heavy rainfall in that region. Ocean transport has also plays an important role in extreme weather on decadal time scale. Our study showed that a reduced northward heat transport in the South Atlantic Ocean leads to a cooler condition in that region, which forces an anomalous atmospheric circulation and brings more moisture from the southern hemisphere to the northern hemisphere, therefore strengthens the rainfall in the northern hemisphere but weakens rainfall in the southern hemisphere. The heat transport in the South Atlantic Ocean has also been identified as a source for heatwave predictability in the US. A reduced northward heat transport in the South Atlantic Ocean can increase the likelihood of heatwave occurrence in the Great Plains 20 years later. Ocean transport also impacts coastal sea level. Because of the Earth's rotation, moving water is deflected to its right. Therefore, the sea level to the right of the current is higher than to its left. The stronger the current, the greater the sea level difference between its left and right. As the current changes, the sea level on both sides of the currents will change. For example, a weaker Florida current flow can increase sea level in Miami by up to 20 centimeters. This poses serious threats as few centimeters of above normal sea level can drive water levels to overtop seawalls and initiate floods. So because of the importance of ocean, the important role of ocean in our climate and weather system and also extreme weather events, scientists have been monitoring ocean changes, looking for warmer or cooler than average waters and strengthening or weakening of ocean currents to help us to predict the short-term and long-term changes in climate and weather. For example, in the past 2 decades, international science community has put tremendous effort to monitor the strength of the overturning the ocean conveyor belt in the Atlantic Ocean at different latitude as shown here. So this is all I have for you today. And our next speaker is going to introduce to you an amazing tool that we use to monitor ocean transport. So I'm happy to take any questions.
Awesome. Thank you so much, for those. So interesting. We do have a couple questions coming in the chat. Somebody would like to know if you could give an example of where somebody could not live without the heat transport from the ocean.
Well, as mentioned, like for the polar regions, you know, like Alaska, I think that would be really cold, freezing. Nobody can live there. And also in the equatorial region, like the tropical region, maybe even Miami, we cannot live here because we get more heat from sun than we radiate heat to the atmosphere. And this will, our temperature will keep increasing and we cannot live here.
Cool. And somebody else is asking, why do ocean currents change?
Well, as Vanellos demonstrated, the density of the water, if the two water has different density, and then that will create a current, and also wind. So at the ocean surface, the wind forcing is, I think it's the main forcing in driving these different ocean gyres. But in the deep ocean, that's because of the density difference that will drive the ocean currents. Like the water tends to flow from the high density water will flow to the low density area. But then because of the Earth's rotation, it will be deflected to its right. So that is kind of complicated how it works. But
A
the
lot of
basic
different factors.
main forcing is the wind forcing and density in the ocean, as well as the Earth rotation.
Very cool. Yeah, a lot of different factors can influence the ocean currents. Thank you so much for your presentation, Shanfu. It was very interesting. And I'm going to pass it off to our final presenter, Grant Rossen, and he's going to talk a little bit more in depth about a technology that we use to monitor the oceans and help with hurricane forecasts.
There we go. Hey everybody, my name is Grant Rossen. I'm a glide and air engineer at the University of Miami Cooperative Institute for Marine and Atmospheric Studies. And I work at AOML for the underwater glider program. So I'm going to show you some of the results and how we get those studies here using underwater gliders. So what is an underwater glider? It's an AUV, which is autonomous underwater vehicle. So it basically acts like a drone, but instead of flying in the air, it flies underwater, it swims underwater. And it can go to a depth of 1,000 meters. And it does that using a variable buoyancy drive, which is, it doesn't have a propeller, you can see, like a standard boat or submarine. So it changes its density, kind of like what Vanellos showed with the density with the salt and temperature, but it does it by changing its volume. It has a bladder filled with oil that it can fill and deflate that changes its volume, and then therefore changes its density, making it more dense than the seawater surrounding it, and that it sinks in the water, and then it uses the wings there to turn that downward momentum into forward momentum. And because it doesn't have a motor like a traditional propeller, it has very low power consumption. And because of that, we can do very long missions, 6 to 10 months potentially. And we need that long time frame because we're using it to study hurricanes. And as everybody knows, hurricane season is 6 months long. So we need to be out there for the entire season collecting this data. So here you can see a short video of a glider in the water. Here it is diving from the surface, and then it'll get down to its target depth of 1,000 meters, here what we call apogee, and then start coming back to the surface. And it'll come back to the surface. As you see here, it turns itself upright. It uses an antenna to start transmit all that data back to us on land. And I always like to say, these gliders, they look really fast, but they actually move really slow. So they only go about a half a mile an hour. So that whole video we just saw from the surface back to the surface takes about 4.5 hours. So what are we using these gliders for? The purpose of this project is try to improve the hurricane intensity forecast. So you see the two panels on the screen here. On the left, there's the track forecast. And you see from 1990 till today, especially in the yellow forecast, that's the 3-day forecast. You see the air has improved from 300 miles of landfall to almost down to 50. So they've really narrowed down where the hurricanes are going to make landfall. But if you see the panel on the right, this shows the intensity of the storm, the air there. And you can see in the last 30 years, there hasn't been much change in the intensity. And the reason for that is that the track forecast is really pushed by the atmosphere. And the atmosphere is relatively easy to measure compared to the ocean because we have satellites now, and then we have these Hurricane Hunter aircraft, which you'll learn about more in the next open house. And they'll actually fly those planes through the hurricane to get measurements and use those measurements to help predict landfall and the track of the hurricane. So the ocean is what drives the intensity of the storm. So the more heat in the ocean, the more energy for the storm to intensify. So that's why it's really important to study the ocean to try to nail that intensity forecast. And you don't want to be out there in a boat trying to collect water samples during a hurricane. So that's why we use these underwater gliders to do it. So you can see here Hurricane Katrina in 2005, and the track as it came over Florida, right over Miami. It wasn't a big storm when it hit here. It was a Category 1. But then it went back into the Gulf of Mexico, and it hit that warm pool of water in the Gulf of Mexico and rapidly intensified to a Category 5 before making landfall in New Orleans. And it was a very catastrophic storm. So now that we have an instrument to do these measurements and we have a goal of what we're going to measure, we needed a study area. So we identified the ocean off Puerto Rico as a place where storms tend to intensify. So we sent our gliders down there in 2014. That's when the project began. And we started taking measurements. And through the years, as we've gotten good results from the project, the array has grown. So you can see from 2014 to 2019, we went from 2 gliders to 7 gliders. And the picture on the right you see was last year, 2020, where we deployed 9 gliders. In 2019, we also started doing measurements in Miami. So we went down to Key West and we deployed a glider in the Gulf Stream. And we flew it from there to Miami. And like I said, these gliders, they move really slow, around 0.5 mile an hour, but the Gulf Stream can move up to 5 or 6 miles per hour. So it's kind of like driving or just trying to walk down the highway. So we're piloting the glider there all the way to Miami, and that distance took only 4 days. And you can see on the right the temperature and salinity profiles we collected during that trip. So in 2020, we were able to do 9 gliders. Even with COVID, we were able to travel down there and get these missions done. So between the 9 gliders, we collected over 970 days in the water. So that's, almost 3 years between all 9 gliders in that time frame. And we did 8,700 miles covered, and we sampled 3 tropical cyclones. And between all those things since 2014, we've done 37 missions in the area. And in that time, we've sampled all these storms, 11 storms, and then plus the 3 in 2020. So that's over 14 storms. Some pretty remarkable ones like Hurricane Maria, which was devastating in Puerto Rico, and Hurricane Dorian, which was very bad for the Bahamas, and Hurricane Irma, which was in St. Thomas and Miami. So what have we shown with this data? So if you look at the data, the blue line here is what the hurricane intensity model, is getting from the satellites and from the airplane. So it can only really measure the surface of the ocean. It can't get any measurements below the ocean because it's not down there. So that's what we're using these gliders for, is to tell the model what's actually happening below the surface of the ocean. So if you see the blue line, that's the model with no ocean data. And then the black line is what we saw with the gliders. So that's what is actually happening. That's the truth. And then the green line is the new model once they assimilate that glider data. So it's still not exactly the same as observations, but it's so much closer. So you can see that in the temperature and the salinity conditions, how much we're improving that model. And so what does that mean for the model output? So if you look at the bottom pane here, you can see for Hurricane Gonzalo in 2014, which was the first hurricane we saw, it went right over one of our gliders to the north of Puerto Rico. So the bottom panel, you can see the model forecast, which is again the blue forecast, and then the black, which is what was actually observed in that gap between the model and the observed. And then once you incorporate this ocean data into the model, you get the purple line, which we showed is a 50% improvement in the model, which went from almost 0 improvement in the last 30 years to 50% with just this addition. So hurricanes are not the only thing we have to worry about while we're out there. We did have at least one instance where a shark attacked one of our gliders. You can see the 4 pictures on the left here of the aftermath of the shark biting the glider. And on the right, that's not actually our glider. That's a glider they deployed for the sole purpose of getting attacked by a shark, and it did its job well. But it just shows you how sturdy these instruments are, that it survived the shark attack and it went 3 more months in the water with no problem. So if you'd like to learn some more about our project, we have a webpage at AOML, and you can see this project as well as all the other ones that were discussed today. Thank you.
Awesome, Grant. Thank you so much. We do have a couple questions rolling in the chat. People are really interested about the hurricane gliders. Somebody wants to know, is that a real glider behind you, or is that a virtual screen?
It's a real glider. But it's just a shell. It's a fiberglass shell, and inside of that fiberglass shell is an aluminum pressure housing, and that's what holds all the electronics and sensors of the glider. And so this is the protective fiberglass shell that helps make it more hydrodynamic and also protects it from shark attacks. And so this is one that we've put together from other pieces that we had that were either attacked by a shark or damaged in some way. So this is the one we use for display.
Very cool. And somebody else wants to know, do you know what kind of shark attacked the glider that you just showed in your last slide?
We don't. The one that we have, we don't know yet. We think it was maybe an oceanic white tip or possibly a mako shark. we recovered 2 teeth from the body of the shark, and we want to send them out to get a DNA test so we can definitively define which shark it was.
Cool. And has a glider ever been damaged by a passing hurricane?
No, we've never lost one to a hurricane. We've never lost one ever, actually. And they're really sturdy, and they stay mostly underwater. So that you see the orange antenna that sticks up here, that's really the only part that sticks out of the ocean. So that's the only part that gets exposed to the hurricane winds, and it's very sturdy, and we haven't had any issues so far.
Very cool. All right, and one last question. Somebody wants to know, what other instrumentation or features would you like to see gliders adapt in the future? Is there more sampling they could do? Could they be out for longer times?
Yeah, so all those are possible. There's a lot of sensors available now that you could adapt into the glider platform. Pretty much anything that you can power and has a serial output, you could adapt to the glider. So there's current profilers, there's acoustic monitoring, there's a lot of biological monitoring. One thing we would really like to see for oceanography is PCO2 and pH, so we can start to look at carbon budgets in the ocean, but the sensors just don't exist yet. So once they do, we can adapt them to the glider platform and start making those measurements.
Very cool. All right, thank you so much for your presentation, Grant. Very interesting.
No problem.
And now, as we wrap up our webinar today, I am going to ask everybody to come back on to screen. Awesome, we're all here. All right, and I would like to thank all of you for your awesome presentations, and thank you for taking the time to be with us today. A big thank you to all of our viewers for tuning in with us tonight. And just a reminder that tomorrow, April 21st, is our Hunting Hurricanes webinar, where we'll learn all about hurricane research. You can register for tomorrow's webinar at bit.ly/AOML-goes-virtual-hunting hurricanes. And Vanellos, did you want to show your density experiment one more time? I believe you said that the temperature tank had mixed.
Well, yeah, if anyone wants to see, it's not yet fully mixed, but you can kind of see that I don't know if you can see that it's purple, and there's like these little diffusive fingers of purple water that are kind of making their way. So I just wanted to show how it was mixing after 30 minutes had passed. Probably in another 30 minutes, it'll be all purple.
Very cool. Awesome. Well, I'd just like to thank everybody one last time for being a part of our open house series, and we hope you stick with us for the remainder of the week, and we will see you tomorrow. Thank you so much to our panelists.
Thank you.